Satellite A has a mass of 1517 kilograms and moves in a circular orbit of radius A, 10.4 times 10 to the 6 meters around a planet. This planet has a mass of 4.2 times 10 to the 24th kilograms, and we're going to assume that universal gravitational constant is 6.67 times 10 to the negative 11th, with units, and the speed of the satellite is VA. How long does it take the satellite to make one complete orbit around the planet? Okay. So first thoughts here is we have a circular orbit, which means that we have a constant centripetal acceleration. So centripetal acceleration will be v squared over r, where r is the radius that's going around. Let's draw a picture real quick. So we have a planet like so. We have a satellite like such. And I'm going to assume that this radius they're talking about, RA, is from the center of the planet. It says around the planet, but they don't give us a radius of the planet. So I can be like, well, they're probably talking about from the center of the planet. Don't know for sure. That's what we're going to assume here. Otherwise, I suspect the problem would be exceedingly difficult, if not impossible. We have a mass of the planet. Check. So I'm going to call this mass planet is 5.2 times 10 to the 24th. Nope, make that look like a 4, okay. And we have the universal gravitational constant, and we have the mass of the satellite. Okay, so we have, zooming in on that guy right there, the satellite. Boop, boop, boop. We're going to have a force centripetal going in. Nope. We're going to have force gravity pulling in, force centripetal pulling it out. And one centripetal, one centrifugal, I don't know. Basically, there's going to be force gravity holding it in, pulling it into circular orbit. That's going to be balanced out by the centripetal acceleration. So long story short, force equals ma. Therefore, we're going to say, click, clack. So force due to gravity equals gravitational constant, mass planet times mass satellite over radius squared. I'm just going to use, we're only given one radius, so I'm just going to call it r. And this will equal m satellite v squared over r, which will be the force centrifugal. Centrifugal, one of those. So either way, so we have the centripetal acceleration v squared over r, multiply that by mass, gives us a force. So now we'll do a little bit of canceling. We're trying to find v, right? How long does it take? Okay, so long. So velocity equals distance over time. You can, the mnemonic that I use for that is my car goes in miles per hour. And so really I'm just doing some sort of dimensional analysis where I know we have to have something that's distance on top and time on bottom. So v equals distance divided by time. In this case, we're going to use meters and we're going to use seconds. So we want to find velocity. Once we have velocity, we can figure the rest out. So what we're looking for then is that guy right there. So we're going to cancel one of the r's, click, clack, because they're the same. And we're going to cancel the mass of the satellite because it's on both sides. And so then v squared equals gravity, mass of the planet over r. And then v will equal the square root of that. So then we want to find the velocity. Yeah, I think we're good with that. So I'm going to start with this. So we do 6.67 times 10 to, I think it's negative 11. Put a little cross in the 7. There we go. Times mass of the planet, which is something times 10 to the 24th. 5.2 times 10 to the 24th. 0.2 times 10 to the 24th. I'm going to assume that's kilograms. And then the radius we gave us was 10.4 times 10 to the 6th. 10.4 times 10 to the 6th. Okay. Yes. So, green, light blue. No, we should do green. Better contrast. Okay. So 6 and 24 minus 6 is 18. 10 to the 6 on the bottom is the same as 10 to the negative 6 on top. And then to combine these, you just add the 24 and negative 6. Then we'll combine the negative 11 and 18 and get 7. And so we are left with, and this is v squared, v squared equals 6.6. No. There we go. 6.67 times 5.2 times 10 to the 7th all over 10.4. Get the calculator. On clear. 6.67 times 5.2 times 10 to the 7th divided by 10.4. And we get 335 something. So this is equals 3.35 times 10 to the, count this up, 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. And speed of light is like 3 times 10 to the 8th meters per second. So our first thought with this is like, ooh, that seems pretty close to the speed of light. Right, that should be the cue that this is v squared, not v. So once you start getting above like 10 to the 6th, you really have to start thinking relativistic. So your spider senses should be tingling whenever you get an answer that's above 10 to the 6th. So 5774.9, which I'm going to call 5775 meters per second, because it's nice and symmetrical. Okay, so we got the speed. So we're looking for time. So time will equal distance divided by velocity, which will be 2 pi times r, which is 10.4 times 10 to the 6th. 10.4 times 10 to the 6th divided by, and we had 5775, not too bad. 5775. I'm going to do this in the calculator. So we're going to do 2 times 3.1415, which is pretty close to pi, times 10.4 times 10 to the 6th divided by second answer. And we have 11,315. 11,315. And this is going to be measured in seconds. So now to convert this over to minutes, we'll just divide by 60. Or multiply by 1 minute per 60 seconds. Same as multiplying by 1. Whoop, don't cancel the 60, cancel the seconds. And that gives us, divided by 60, 188.6. 188.6 minutes. Whoop, so 3 hours. Good for us. I feel accomplished when the answer that I get is actually a possible answer. Very self-reassuring. Okay, so now we're going to assume that satellite B has twice the mass of satellite A and moves in an orbit with the same radius. Which of the following best describes VB, the speed of satellite B? Okay, so first thing we're going to do is we're going to look at our formula over here. So this is our formula. V squared, which is similar to V in this case, is going to be gravity constant times mass of the planet divided by radius. And you can see here that up here the mass of the satellite canceled. And so basically the mass of the satellite helps pull it towards Earth, but also the mass of the satellite, the centripetal acceleration is causing it to fly off. So long story short, they cancel each other out, and the mass of the satellite is irrelevant. Therefore, velocity of satellite B will be the same as velocity A. And that's one of the reasons why you should write out your equations like this. That way, when you have follow-up questions, like, oh, okay, pretty straightforward. Now we have satellite C, which has the same mass as satellite A and moves in an orbit with twice the radius. Which of the following best describes velocity C, the speed of satellite C? Okay, so RC equals 2RA, okay? Let's see here, twice the radius, okay. So if we look at our equation here, if we put in a 2 here instead of the 1R, so if we had 2R instead of 1R, that would mean that the velocity squared would go down. Specifically, velocity would go down by square root of 2. And so the velocity at a greater distance will be less. And so the velocity of c will be less than velocity a, and specifically it'll be less by a factor of 1 over square root of 2. And that we just get from our formula right here that we wrote for v squared equals gravitational constant times mass of the planet divided by the radius of the orbit, circular orbit specifically. Now, if you had time and you wanted to be sure, you could plug that number in and actually solve for the speed. I'm not going to, but you could if you had time, and it'd be a good idea. If you don't have time, don't do it. Okay, so I hope that helped. The idea here was we just balance the force of the centripetal acceleration and the gravity, put them together, do some solving, some algebra, and it all kind of works out. So it's not too bad. This one's, once you have the basic setup for this and have the picture drawn, it's pretty reasonable, not too much deep thinking, but still a good problem overall. And I hope that helped. See you next time.